Okay, this is 1.1 continued. We're going to look at the square root of x, parent function. So what does this graph look like? Well, if we make our xy chart, we can look at -2, -1. Now, when we look at those two, we're going to actually pause at this one at 0. So when we look at -2, well, we can't take the square root of a negative number, so it doesn't exist here. Okay, it's not a real number here either. So that one, we can't have anything there. Okay, but square root of 0, we can have a 0. Now we could continue with 1 too. However, in this case, I would continue with 1 because I know square root of 1 is a perfect square of just 1. If I did 2 though, I'm going to end up with a decimal. But if I do square root of 4, for example, that's a perfect square. And so that's what I'm going to choose next is 4. Square root of 4 is 2. If I wanted to do one more, I'd take the next perfect square up, which would be square root of 9. Square root of 9 would be 3. So let's go ahead and graph those. We've got 1 point at 0, 0, 1 point at 1, 1, 1 point at 4, 2, and I'm going to leave it at that because that's all the room I have. So that's our parent function. Okay, cube root of x, we can do the same thing. This time though, I'm going to choose numbers that are a perfect cube. And that means what are numbers that a number times itself equals them, or a number times itself 3 times equals that number. So for example, let's start with a -8. If I have -8, well, I know -2 times -2 times -2. Let's check this. -2 times -2 is 4. 4 times -2 does equal -8. So that tells us -8 would be a perfect cube, and the answer then would be -2. Okay, next let's look at -1. So we have -1 times -1 times -1 equals -1. So -1 would be the cube root of -1. Notice the difference between the square root and the cube root. The cube root, you can do a cube root of a negative number, where the square root you can't because it's only a number times itself. So basically it's even, and so those negatives don't have a chance to cancel out. Where if it's a cube root, this is odd, and so there are 2 negatives that match up, but there's always going to be one left over, and so you can have the cube root of a negative number. Okay, let's look at 0. Cube root of 0 is just 0, and then we'll just use 1 and 8 again. Cube root of 1 is just 1. Cube root of 8 is 2. So if we graph this, so we have -8 is at -2. -1 is at -1, 0, 0, 1, 1, and then 8, 2. So we're going to have something like that. It's not perfect. If you want to see a better one, you can always go to Desmos and graph it. So we have kind of a curve here. Okay, 1 over x. Let's look at this one. So let's do, we could actually just do this again, -2, -1, 0, 1, 2. That does kind of give us a good idea. So 1 over -2, we just get -1/2. 1 over -1, we get -1. 1 over 0 does not exist. 1 over 1, we get 1. 1 over 2, we get 1/2. So let's look at what we have. This is a different kind of graph. You may or may not have seen this one before. So, okay, so we're at -2, -1/2, -1, -1, and it doesn't exist at 0. And so that tells us we're going to have what's called an asymptote there. So basically a place that doesn't exist. So we'll have a graph. It actually curves there. It's not a point. Okay, and then similarly we'll be at 1, 1, 2, 1/2, and so we'll have a line that's kind of approaching like that. Okay, 1 over x squared is going to be similar, and I will leave that one for you to do. Okay, let's look at graphing these two. So if we have a -2, -1, 0, 1, 2, so we graph this, we get -2 squared plus 3, we'll plug it in. So remember, a -2 squared becomes a positive 4, because -2 times -2 is a positive number, plus 3, we get 7. -1 squared plus 3, -1 times -1 is a positive 1, plus 3, we get 4. 0 squared plus 3, we'll just end up with 3. 1 squared plus 3, you'll notice we might be repeating here. So 1 plus 3 is just 4. And you probably have a guess for what that last one will be. 2 squared plus 3, still a positive 4 plus 3. And so we get 7 there. So -2, 1, 2, 3, 4, 5, 6, just enough. We're at 2, 7. We were at -1, 1, 2, 3, 4, and 1, 4, and then 0, 3. And so we're going to have a graph that looks like that. Notice from the parent function, if you look back at the parent function was a graph that went through these points. So notice this one just went up 3. So this plus 3 on the outside just made it go up 3. So let's look at this one, see what happens. Oh, actually, let's undo that. Because we have a square root, I'm remembering we can't do a negative under that square root. And so we want to do numbers that will give us a perfect square. So let's start with 0. Then let's maybe do 4, 9, 16, and 25. So I'm just going to go in order. So square root of 0 minus 2, we just get 0 minus 2 or -2. Square root of 4 minus 2, square root of 4 is 2. 2 minus 2 is 0. Square root of 9 minus 2, square root of 9 is 3. 3 minus 2 gives us 1. Square root of 16 minus 2, square root of 16 is 4. 4 minus 2 gives us 2. Seeing a pattern here? Square root of 25 minus 2, square root of 25 is 5. 5 minus 2 is 3. So the problem is we're not going to have room, are we? So we'll be at 0, -2. We'll be at 4, 0. We'll be at 9, 5, 6, 7, 8, 9, and 1. So that's going to give us enough. I'm just going to, go from there. Okay, so that one you can see similarly, square root of x is kind of right through here. And so you can see it just shifted down too. Okay, let's look at 1.2, Introduction to Functions. So a relation is just a set of ordered pairs. So basically anytime you have that set of ordered pairs, that's a relation. Now, a function is a special kind of a relation. We'll talk about that in a minute. So the domain of a relation is the set of inputs or the first component in an ordered pair. So basically the x value in the ordered pair. The range is the set of outputs or the second component in an ordered pair. One way that I keep this straight is D comes before R in the alphabet and X comes before Y. So domain goes with X, range goes with Y. So a function is a unique relation. It's a relation in which the input has exactly one output. So for example, each person only has one birthday. Revenues a company makes is based on the number of cells. Okay, so let's look at these examples. We need to determine if the relation is a function. So basically, does each input or x value have exactly one output? So Arkansas goes to 4, Texas goes to 32, Oklahoma goes to 5, and Oregon also goes to 5. So would this be a function? Well, if you look, all of the inputs have exactly one output. We don't have one input going to 2 different outputs. And so yes, number A would be a function. Okay, let's look at this one. So we have -3 going to 7, 1 going to 7, and 2 going to 2. So this might be tricky. We might be tempted to say it's not a function, but because all of the inputs go to exactly one output, or another way to look at it is we don't have any repeating x values, this one is also a function. Okay, let's look at example C. We have 1, 2, 0, and 0. So 1 goes to 6, 2 goes to 6, that's not a problem. But 0 goes to 3 and 0 also goes to -2. Another way we could look at that is we could list our inputs and then list our outputs. Excuse me. So 1 goes to 6, 2 goes to 6, and that's okay because notice there's just one arrow coming from each input. Basically there's just, the input just has one output. But here, 0 goes to 3 and 0 goes to -2. So we have 2 arrows coming from the same input. That tells us this input has 2 outputs, so that's a problem. So no, C is not a function. This one we have A goes to 4, C goes to 32, B goes to 10, C goes to 5. What do you think on that one? Is a function or is not a function? Well, this one, no, it's not a function because you can see C is going to 32 and C is also going to 5. So one input has 2 outputs. So that one would not be a function. So another way to determine if a relation is a function, or in this case the graph, is we can use the vertical line test. So if no vertical line can be drawn so that it intersects a graph more than once, the graph is the graph of a function. Okay, so let's look at these. On example 2a, we can see anywhere that we draw a line, we don't hit it at more than one point, and so yes, this one is a function. Same thing here, we draw, there's nowhere, if we draw a vertical line, we won't hit it at more than one point, so yes. This one, almost anywhere we draw a line, we hit it at 2 points, and so this one is not a function. Okay, here, this is close. It looks like you almost hit it here. You hit the same point twice, but you just don't quite. You'll just hit it once. And so yes, this is a function. Okay, what about here? Nope, we're hitting infinite number of points. So that one would not be. Here, anywhere we draw a line, we don't hit the graph more than once. And so yes, this is a function. Okay, this one, we've got a point at 1, 2, 3, 4, 5, 6. So we can see anywhere we draw a line, we're not going to hit more than one point. In this graph H, well, it looks like right here at 2, we're going to hit 2 points. And so here, this one was a function, but this one H, we hit 2 points. And so no, that is not a function. Now we didn't find the domain and range of those last relations, but the x values are the domain, the y values are the range. So one way that I like to look at the domain and range is I like to imagine a stick or maybe even your pencil. Okay, we'll draw a little pencil over here. And we're moving it from left to right. So this can help us find the domain because we basically want to see where does the x value start and where does it end. So you can imagine this graph is going, and it's going forever in that direction. So there's no x value it's not going to hit. It might be really high, it might take a while, but this one's going to be all real numbers. And so the way that we would say that for domain is we would say -infinity, because that's the smaller number, to +infinity. Now around infinity, we always have parentheses. Okay, let's look at the range. So we're going to do similarly, but imagine your pencil down here and we're moving up. So we want to see what's the first value we hit. Well, it looks like it's 1 for y. So 1's the first value. It is including that. It's not an open circle there. And so we will draw a bracket to show we're including 1. And then similarly, we can see this is going to go on forever and there will be an infinite number of y values. And so it'll go to infinity, again, a parenthesis. Okay, let's do part B. So we have, imagine our pencil moving left to right. The first point we hit would be at 1. So the domain starts at 1 with a bracket because it's including. and it goes on forever, so infinity.